Hello, everyone. Let's start on time. This is not Deutsche Bahn. You're here for a talk on virtual threads and the things that go around it. And so my hope is to go a little bit deeper than your typical blog article and actually show you a few things that go on under the hood. So I'm Cay Horstmann. I have written a book called Core Java that now is in its 13th edition. It was, all modesty aside, probably the first Java book that actually truthfully said what was going on in the platform, and I hope it still is. I'm a Java champion. So back to what you're really here for is virtual threads. So as you probably know, there are now two kinds of threads: platform threads, the kind of thing that we've had ever since Java 1.2, and virtual threads. And virtual threads run on regular platform threads. And when a virtual thread blocks, because it calls on a socket or on the lock, then it gets kicked off the carrier thread, and another virtual thread runs on that same carrier thread. That's not really a complicated project, complicated concept, and it's also it's cheap. Right now, you're kind of worried about making a blocking call, maybe, because it uses up a platform thread, and platform threads are a limited resource. You might have like 10,000 or so of them, and so if many of them are used for nothing but waiting for something else to happen, that's really expensive. But a virtual thread, there's almost no cost involved in blocking it. We'll explore a little bit more on what residual cost there is. So why are they called virtual threads? It's supposed to remind you of virtual memory. So as you learned in OS class, the operating system might like page out some memory to disk, or at least it did when your professor was young. And so it's the same kind of thing, that you have many more virtual threads than you have actual threads, just like at least it used to be, and I guess in some platforms it's still true, that you might have more virtual memory than you have actual memory on the machine. Do not think virtual function. When I first learned about virtual threads, I somehow thought, well, what's it got to do with virtual function? It has nothing to do with it. Naming is hard. So if you are as old as your professor, you might remember green threads in Java 1.0. And you might say, didn't we have all of this stuff before? Because a green thread was one that was multiplexed on a platform thread. But at that time, when the green thread blocked, then it also blocked the underlying carrier thread. And since there weren't very many carrier threads, multi-threading in Java 1.0 was really more of a proof of concept than something that was really usable. This is final in Java 21, so if you're using Java 21 in production, you can start using this stuff tomorrow. And so the question that I'm hoping to answer in the next 30 minutes or so is whether you should. A couple more concepts. There's a thing called a scoped value that is, it's similar to a thread local. It's there so that you can have thread-specific values, so that each thread has its own copy of a particular value. If you've ever used thread locals, you know there's always a danger that you put a thread local and then you forget to clean it up, and then the next task that runs on your thread can observe what's in that thread local, and that could potentially actually be a security risk. And so I'm not going to go through the syntax example right now because we're not having a ton of time. I just put it here on the slide in case you want to read the slide. Oh, I should also say, and I'm going to jump back to the first one. If you want to take a quick photo of the URL, you can read the slides at the comfort of your home, and you can also download all of the source code for this presentation and run it yourself. There are clear instructions on the slides on exactly how to run it and to reproduce what I won't always have time to do. All right, so we're going to be talking about why you might want to use these scope values. It is an important part of these three things that are there to make virtual threads happen. And it is final in Java 25. Then there's the third thing called structured concurrency. Oh, by the way, if you have a question, every slide has the barcode on there, so then just put the question in there and I'll get to them at the end of the talk. So the third aspect is what's called structured concurrency. there's a nice article by this guy, Nathaniel Smith, who programs in a 6-letter language. And he said that, and rightly so, that if you start a thread, that thread runs, and you don't really know when it's going to be finished, or if ever, and what resources it accesses. It's kind of like Goto in a programming language from the 1950s. In the 1960s, of course, everyone said Goto is bad, and we replaced Goto by these structured constructs. And so he says in concurrency you should do the same thing, and that's what he calls structured concurrency. And the idea is that whenever you branch off into new threads because you want to do things in parallel, then inside your programming construct, inside the code, one should see when they come back together. That should happen at the same place where you launched the threads in the first place, and that way you now have a very clear idea when do these threads terminate. You also have a way of saying if some of these, for example, if they fail, then you could easily cancel the remaining ones if the failure is fatal. You know what resources are managed. That's what's called structured concurrency. We are getting this in Java right now in the 5th preview in Java 25. So this will not be ready for Java 25 is an LTS release, so it will not be immediately available, but it will eventually come. And it's implemented as a library, not as a language construct. It's called a structured task scope. You call open, and it gives you this mechanism that you use to manage your threads. Then inside the scope, you call fork to start a new thread. So that makes this one. The next call to fork makes this one. Now I should have done 3 here to match the picture. Then you call join, and join is a blocking call. Don't worry, blocking is cheap on a virtual thread. It's a blocking call that waits for the forked threads to complete. And afterwards, then you can call on the subtask objects that the call to fork gave you. You can call get to harvest the result of them. And then you do whatever you want with the results. If one of these tasks fails, then the others automatically get canceled in the call to join. And so you don't have to worry about doing that cancellation. There's various mechanisms. In this case here, this is the most common mechanism where the expectation is that all forked tasks must succeed, and if any of them fails, the whole thing fails. But you could also imagine other policies where maybe you run them in parallel and you're happy with any of the results, and you may or may not care whether some of them fail or not, and so you can pass different completion policies to open. That, in a nutshell, is structured concurrency. So we have these 3 things: virtual threads, scope values, and structured concurrency. And the question is, is it any good? Do we want this? So the first round of blogs a few years ago always had a code sample that ran 1 million virtual threads. And then they showed if they were platform threads, you would plain run out of memory because you couldn't allocate that many of them. And wasn't that amazing? But really, that is probably not your use case. Right now, I don't think that you have that the kind of business work that you do will actually scale to 1 million concurrent users on a single machine. So the million is probably too much. But if you could do 20, 30,000, that might be pretty good, because right now you're definitely constrained by the number of platform threads. And if you really do run 10,000 platform threads in a microservice, then you pay quite a bit for that. So so somewhere between 10,000 and 1 million, there is a sweet spot. And so really the reason, and also some people think that somehow virtual threads run tasks faster. It is not that the virtual threads can magically accelerate the silicon. So they run on regular platform threads. So you can never expect that the virtual thread tasks will themselves complete faster. The reason is you can increase throughput, because if you have lots more tasks than you have platform threads, and those tasks mostly block, then nothing is happening and more work can be done, which means that you get a higher throughput. You might easily get like 100,000 concurrent users, where right now you have 5,000. And so that could be nice, depending on the kind of application that you have. We'll talk about that. The other reason is, in the past, you may have been told that you should change to a reactive programming style. and that all the cool kids code reactive, and reactive is functional and therefore intrinsically good. And so you might have gone to some training on how to do reactive programming, and it's actually a big pain in the neck, and it's not easy to maintain, and it's unnatural in so many ways. And why do people do it? Because it is another approach of having more throughput with a finite number of platform threads. But the coding is so unpleasant that Kotlin, for example, or JavaScript have an async await mechanism to make the coding easier. Java, on the other hand, has said, we're going to do none of this. We're simply going to let you code in the way that you've learned to code in kindergarten, with loops and function calls and exceptions. And you instead of saying, when this thing happens, then do that, then you simply wait for it to happen, because blocking is cheap. So as long as you don't have to pay for blocking, there's no particular reason not to just call methods and wait for them to complete. And that is the biggest promise of virtual threads, that you don't have to redo all of your work in this reactive style just to get better throughput. You can get better throughput simply by switching to virtual threads. So there's an API for creating and starting virtual threads, and I'm not going to show it to you, because when is the last time you created your own thread? When you actually physically called new thread.start. It's not something that you often do outside a toy program. In fact, normally, how do you get a thread? You get a thread because Quarkus or Spring or whatever runs your business logic on a thread that they created. And so each of those frameworks has some way of doing it. In Spring Boot, you simply say, I want the worker threads to be virtual, and you set some configuration flag somewhere. In Quarkus, they make it a little bit more fine-grained, for reasons, where each service method has to have an annotation that says, I want this particular method to run on a virtual thread, and then that's exactly what happens. But either way, your business logic will run on a virtual thread when you ask for it. And so I'm going to just run just a silly little example here. Let me find here where I have this. So we're going to do the typical demo where we're going to sleep. So I'm having a task that sleeps, and that then returns the name of the current thread. And here I'm doing it on a virtual thread. Here I'm using Quarkus because I have this fine-grained control here. Here I'm doing it on a platform thread. And so when I run this thing here, I'm going to have to start up Quarkus, my little app here, and I'm using enable preview because for a couple of the features I'm using some preview features. If you don't do that, you don't need to worry about that. So let's just I don't want this. Yeah. Here's my platform thread, and here's my virtual thread. And if you look carefully, you saw there was a 1 second delay. And you can see the thread IDs look different. The platform thread is just the same thing that you've seen before. The virtual thread tells you that it's running on this particular platform thread, on fork join pool -1 -worker, as it turns out. All right. So why is throughput better? So here is my little diagram that I'm hoping I can get AI to clean up one of these days. So in the traditional way, you had thread pools, right? And the thread pool would run your first task until it blocked, and then, well, what could it do when the first task blocked? It couldn't really do anything. It sat there, and it also blocked. And eventually it was done. And so you could run a few tasks in parallel, but when one of those tasks blocked, there was really nothing that the thread pool could do to compensate for that. So each of these dashed lines here means blocking. Whereas if you use virtual threads, these things that used to be your pool threads are now the carrier threads, and you can run many more tasks on them because all of these blocking things can now be filled up with more instances of the virtual threads. So you're going to get higher throughput. That's just the way it is. And so the idea of virtual threads is to minimize the blocking that you had before. Now, before you had a thread pool, why do you have a thread pool? You might have like 100 worker threads there that would be used by the incoming requests. The incoming request would be piled up. Eventually, one of the pool threads was done. It would then be used to serve another instance. It would then take that other instance, like here, and it would start running it. Then that task would block, and the pool thread then was condemned to blocking as well. That's why you had 100 or so of them, but it limited your throughput, right? Your throughput is strictly limited by the size of your pool. Virtual threads don't have that limitation. Also, virtual threads are themselves not pooled. You always just make a new one. There's no sense in pooling virtual threads. You're not doing that in the first place, so you probably don't really care. When a task comes in, it'll instantly be mapped to a virtual thread. That virtual thread might have to wait until one of the carrier threads is ready for it because another one blocks. That's the way it is. Yeah. So let's just stress test this thing here a little bit so that we can see how to do this. I'm using one of the stress test things that's simple to use. Just that you can kind of get a feel for how you can do these things yourself. So I am now going to do 1,000 requests, all simultaneous, with a timeout of 60 seconds, and I'm hitting the platform thread version of this. And now you can kind of see it chug along. And we see in the end, it did them all. That's good. And we see what the throughput is. Let's do the same thing with the virtual threads. And it's much faster, as you can see. Because with the platform threads, I think Quarkus gives you like about 200 or so. So the first 200 ones go to sleep, and then nothing can happen until that second has elapsed. And then the next batch of 200 comes along. With the virtual threads, they all get scheduled right away. They all sleep right away. And you're done after a second and change. So that's nice. So virtual threads are great for these blocking tasks. So what if you do something that's processor intensive? So I'm having another service here, and you can look at the source code. It searches through the Java source code for an instance of a word. So I'll just do this one here and use. Let me just curl it, and then you see what it does. So you can see it takes some time, and these are the names of all of the files in the Java API implementation that have the word record in there. That may mean because they actually use a record or because it's somewhere in the comments or something. But there's quite a few, right? So now let me do a bunch of those. And I'm only doing 100 for obvious reasons. And so you see this thing with platform threads, it takes kind of a long time. And when we do this with virtual threads, I've made the route so that virtual, as you expect, goes to virtual threads. You can see you get some results a little bit faster, but overall, we don't have to wait for the final actual number. The performance is not really dramatically different because this is a task that is, it's really pretty much the same performance. This task does not block. Most of the time spent is actually going through every file in the Java implementation to see whether it includes this thing. So for a non-blocking workload, there's no advantage in using virtual threads. So if you have a task that just crunches along for a long time, virtual threads give you no advantage. On the contrary, they give you a disadvantage. A virtual thread that is working, that is not blocking, cannot be preempted. There's no way of interrupting it. no easy way of interrupting it. Whereas a platform thread, it'll run for a while and then the OS preempts it and something else can happen. So don't use virtual threads for workloads that don't block. There's a whole bunch of articles that you find out there where someone says, I use virtual threads and they did me no good at all. And then you look at what they were doing. Well, they were mining Bitcoin or something on each thread. And at that point, you want one thread per core and that's it. Yeah. All right. So I'm going to give you a few tools on how you can watch the threads. And so here is one thing that you can do, and in the interest of time, I'm going to omit the actual demo. You can make a Java flight recording, and then you load it into Java Mission Control, and you can observe a little bit what these things are doing. So I have prepared this here, and so we're going to be looking at here is Quarkus with non-virtual threads. And so what I'm seeing here is I'm doing that same workload where these threads are sleeping. First of all, you see that I have about 200 threads that Quarkus uses to run those 1,000 incoming tasks. And you can kind of see what they do. They sleep. Right? That's, after all, what I've told them to do for a second. So when we do this with virtual threads, okay, come on, I don't want this. I want my... here. Then you can see that there's a lot of action because as soon as one of the carrier threads, first of all, how many carrier threads do we have? Here you see them. Here are the carrier threads. You can see apparently I wasn't very good with doing the recording. The action only started here. But here's where things started. And there was some busy activity. And later, of course, there was a lot of sleeping because my workload was not very intensive. But you can see that where that higher throughput comes from. So the flight recording tool is a great way of visualizing what goes on. You can do it with your application because, as you can see, I've just run Quarkus, and then I've told JCommand to start the flight recording. So you can do that in the lab with your own projects and observe what your threads are doing. All right. So notice that here you do not see the virtual threads. You only see the carrier threads. There is a way of also seeing the virtual threads. Not so clear how useful that is because you will probably have many of them, but you can turn on the events here for it, and I've shown you how to do this. More interestingly, let's look at the non-virtual threads here for a second, and let's look at the garbage collections. And what you see is there was no garbage collected, which you would kind of expect because there was no work done, right? It all just called sleep. But when you look at the virtual threads and look at the garbage collections, then you can see that memory steadily crept up, and there was a fair amount of garbage collection activity. The reason for that is that the virtual threads, the stack frames are collected. So on a regular thread, you have a stack frame, a pretty large stack frame actually, but that's part of the physical stack of your process, and that's off heap. Whereas the virtual thread, as soon as the virtual thread gets suspended, its stack, which is only the Java stack, which is not normally large, but it does get tossed into the heap, and when the task is over, then it gets collected. So with virtual threads, you always have to worry a little bit about that pressure on the garbage collector. So we can ask how much memory is being used, and in the interest of time, I'm not going to do this for real, but the tool is again JCommand, and when you do that, you can see that with virtual threads, this particular app here used 64 meg, and with platform threads, it used 1.9 gig. Which is different. And the reason for that is that on each platform thread has 1 meg of memory, about. And so if you had 200 of them, that's what, 2 gig? No, 200 meg, right? Yeah. So anyway, so I've actually, and this is not 2 gig, I think this is 200. Okay, whatever it is. You can compute it, and so, but you can really see that the platform threads are an order of magnitude more than the virtual threads, And so if you have like 10 times as many virtual threads, you get 10 times the throughput and no penalty in memory. If you, of course, have 100 times as much in virtual threads, at some point, then you generate a good amount of heap, and also heap is more costly because the garbage collection is more costly than just reclaiming the stack memory. So it's something to pay attention to. And yeah, so again, virtual thread stacks are small. That's the thing to remember. You can afford to have many of them, but of course not an infinite amount. All right, so the increased throughput is not totally free. Observe and measure. Now here's the thing that most people run into pretty quickly once they say, oh, we're going to start using virtual threads. We're getting better throughput. We're having less memory. I've talked to people who say that memory saving them alone is great for them. They don't even necessarily care about the throughput, but they now can run this on a smaller VM, and that means less money to AWS or whoever. And so then they do have more throughput, and then they realize that now it puts pressure on the resources that they use, the database or external services or something. And the reason is that virtual threads, they're not throttled by anything. So far, when you use Quarkus or Spring or whatever, your implicit throttle is this thread pool. If you have 200 threads on that thread pool, you're never going to have more than 200 concurrent requests to your database. Well, for the database, actually, it doesn't much matter because the connection pool can perfectly handle that all by itself. You don't have to do anything there. You have to size it somewhat appropriately. And if 1,000 virtual threads just gang up on that connection pool, that's fine. They all block, but blocking is cheap. But in other cases, you may need to do the rate limiting that was free for you before. So I have a little example here where I have this nifty little service here that that gets you a random image, something you've always wanted to do. Here, that is the random image of the day from Wikipedia. And so now if you want to get 500 of them, and then the trouble was that it quickly, like instantly did that with virtual threads. But unfortunately, when you look at it, about 20% of them failed. And the reason is that Wikipedia is actually not built to have 500 incoming requests from the same address. I used Wikipedia because previously Heinz Kabutz did a thing like this where he used Dilbert, and A, it's no longer politically correct, and B, Dilbert then will ban your IP address for a good long time. So that's not so good. But it's a real problem that you would have. You call out to an external service. That service was not meant for a huge concurrent a set of calls, and then you need to limit it. It's easy enough. You can do it with a semaphore, like they taught you in school. And I'll give you the complete sample code of that, and that works. But you just need to be aware of the fact that if your app is built so that it does branch out to other calls, that you may be called upon to do a bit of rate limiting there. It's not hard, it's just something you have to know. And that's also a common complaint that I hear from people, that they just never really thought about it because before the app was so throttled by the thread pool that they've never seen it go wild. All right, so the next thing you hear is this thing called pinning. So normally a virtual thread is parked when you have network I/O or sleeping or locking, except up to Java 23 when one used a synchronized lock. There's two ways of locking in the VM. There's good old synchronized from Java 1.0, and then there is reentrant lock from Java 5. Now, you've probably not really done much with either of those, but in the implementations of your various services, people have made that choice one way or another, and many of them foolishly have used synchronized because that's what they learned in school. So they would have been better off using reentrant lock. And now, and for technical bizarre reasons, in Java 21, 22, and 23, the synchronized ones have this phenomenon of pinning. And so it's often not really a problem. So there's a whole bunch of synchronized in like concurrent hash map, and nothing happens inside the synchronized. So you don't have to worry about it. But one does have to worry about if there's a synchronized and then there's blocking going on inside that. Now, how the heck would you know? And so if that were to happen, then the carrier thread would be immobilized, and that really can hurt your throughput. And it really does happen if you get a third-party library, and of which you have many, right? There's JDBC drivers, or you might be doing something with AWS and S3 or something. You have a driver for that. And inside those, there might be some pinning, so you need to be able to observe it. So, and it's easy enough. You run your code with a particular flag, and then each time the pinning happens, you get a stack trace. And in the interest of time, I'm not going to show it to you, but trust me, if you were to run the sleep pin, which simply sleeps inside a synchronized block, then that stack trace will show up there, and you can see that this happens. So it's something that one needs to monitor for. Of course, if you use something like Quarkus, they have solved these things with essentially everything that they have going for them. It would more happen if you had some goofball third-party thing these days. But you really do have to have up-to-date JDBC drivers, up-to-date AWS, and all of that. So there's ways of doing this, and again, in the interest of time, I'm not going to do that. It could also happen when you call native methods or foreign functions. And again, you are probably not really going to do that in your code so much. Maybe it'll happen in some library code. Again, it's something that you just need to pay attention to. Now, you will say, why doesn't it just give you more carrier threads? Because for two reasons. One is they said that you should really control the pinning, and the other thing is in Java 24, this problem has been completely solved because now, after a whole bunch of engineering work, they made it so that the synchronized blocks, they no longer pin the carrier thread, but that the suspension mechanism works fine. So if you're using Java 21 in production now, and you're eager to use virtual threads, then you need to pay attention to it. If you're saying, well, this is research right now, and eventually I'll use it, then Java 25 is coming out soon, and you no longer have that problem. One thing that you often hear is that if your program does a lot of file I/O, then you might have issues. Now, socket I/O, calling like a database or an external service, a REST service, no worries at all. Socket I/O is fully asynchronous. It works beautifully with virtual threads. They get parked, and another virtual thread can get executed. But file I/O is not asynchronous in the Java platform. And so what they tell you in the docs is that if you do file I/O, it could happen that A, it's synchronous, so when it does block, and B, to compensate for that, they might give you more carrier threads. So I have tried very hard to see this. So I have a little sample program here that runs 10,000 virtual threads that do a crazy amount of file access. And I wanted to show you that when I attach JConsole to it, and where you can see all of the threads in real time, that out of 7, it's not just 14. I have 14 cores on my laptop, but that it would expand. And I have never been able to do this. I have talked to dozens of people. None of them has ever seen it. And finally, yesterday, Alan Bateman told me, yeah, it is only for this very, very narrow subset. You need to make a synchronous read or write. I didn't even know how to make one, where you use a random access file with a D flag. It's very unlikely that this is really going to happen. So don't worry about file operations. I'm going to go ahead and measure it, but I would not really get bent out of shape, even though every blog will tell you that this is a potential problem. It probably isn't. So what about reactive? If the reactive people will tell you that reactive is great. It eliminates callback hell. It is declarative. It can handle back pressure. Well, virtual threads take care of callback hell. The declarative style is not an unalloyed blessing. And if you have back pressure, well, are you really doing back pressure to the point where you are signaling to the other end that you wish to have your rate reduced by 30%? Or are you simply saying, well, don't give me any more? If you just don't want any more, then you use a bounded queue like they taught you in college. And sure, then you have blocking calls, but blocking is cheap with virtual threads. So you can have the advantage that is cited for reactive programming in almost all normal applications with much less of a hassle. So I have a trivial benchmark here, and you can run that, and you'll find that if you run the reactive version using Quarkus reactive whatnot to do sleeping, it sleeps just as with just as much throughput as it does with virtual threads. Now, sometimes you'll find some papers where they claim that reactive is strictly better, and so I have a link to one of them here. And when you look at the details, then it turns out that what these guys did in this particular paper, they said, if you push the load so crazily that both platform and virtual threads really suck, that then the platform threads suck less. But it's not really something that is characteristic of a typical workload. There's a lot of, whenever you look at one of these actual benchmark things, try to find out what weird angle it is at. So I've seen them on either that end where you have completely unrealistic heavy workloads, or we have completely unrealistic light workloads, and then they come to whatever conclusion they want to come to. But it really is, and it's unclear in this case, what the issue is. So they say there's more GC with virtual thread, undoubtedly. They say that Netty might not be as optimized for virtual threads as it should be, which is also true, but might not be true forever. So go ahead and measure that. I would not say I'm going to stick with reactive or go to reactive just because this one white paper. It's easy enough to measure it on realistic workloads in your applications. Next thing, structured task scopes. Should you use them? So the idea of structured task scope is, like I say, you have multiple things that you want to do in parallel. You call business service A, you call business service B, and business service C. You need to have all of those answers from all three in your hands before you can decide what the next step is. Could happen, right? And what do you do right now? Are you currently running them in parallel? Well, if you do, then that's good. You might have had like an executor service and schedule them on them, or use like a Jakarta EE concurrency construct or something. If you do that, then you're absolutely interested in structured task scopes because they do it easier and cleaner. If right now you say, well, I've really never done that, I've always just called one and then the other and then the third because it didn't really matter that much in practice, then you can still now use it structured task scopes easily, but probably there's no burning need that you see. So they are nice. They're absolutely nice. But you would feel the need to use them if right now you have created threads in your own business logic, which not that many people do. Thread locals. So that's another thing that strikes fear in the heart of people who think about virtual threads. So every thread has a table of these thread local variables, and there are two use cases that you hear. Like, what if you have like an object mapper from like a JSON object mapper? It's a bit of a heavyweight thing, and do you really want to construct one each time you need it? It would be nicer if you could just use a global one. You can't use a global one because they're not thread safe, but if you could use one per thread, you have 200 worker threads, now you have 200 object mappers. That's better than, say, 10,000 object mappers, so why not? And so that's kind of a use case. The other use case is that you can avoid passing lots and lots of data deep into the calling hierarchy. So that sometimes that happens with context or database connections, or I've seen it with instrumentation that wants to, like open telemetry, puts thread locals into your business code. And so those are legitimate use cases where you kind of want to have these implicit parameters. And so if you have 200 worker threads, then you have 200 copies of each of these objects, not a problem. Well, if you have tens or hundreds of thousands of threads, you can perfectly well have thread locals with virtual threads, but then they get to be more expensive. So the first question is, how do you even know if you have one of those? And so there is a flag that you can see. You get an exception if one of them gets set, and that gives you an indication. But I was actually kind of curious to see what would happen in Quarkus. Does Quarkus actually give me any thread locals? And so I gave a class, and I wouldn't have time to demo it right now, but you'll find the source code if you want to do the same kind of spying. You can actually use reflection to spy on the fields in the thread object where the thread locals are, and you can print them out. And so For that, you have to be a little bit more brutal about defeating the module system here, something we always enjoy doing. So I'll just do this here, and we'll just see what we have in virtual threads. Oops, am I not running it? I'm sorry? Okay, I'm not going to figure out in real time. What you would find is, and it's easy enough for you to replicate this at home, what you'll find is, yes, there is a thread local that Quarkus gives us. Thank you, Quarkus. And it's actually kind of big. So I added this verbose thing here, and then it goes through reflection inside, and you can see all the fields in it. Is it necessary? I don't really know. I mean, the Quarkus people know what they're doing, but it is, and you know, how much of that is shared, I really don't know, but it's something that one does need to measure. So, and it's also true if you then run something like open telemetry, it adds more things to that. So you do need to understand what the impact is on your application. So I can only give you the tools to do it. In practice, people have been using virtual threads on Quarkus and on Spring just fine with these thread local objects. So it's an engineering trade-off. It's just something that you want to know. Very few people use them on their own. I mean, you would know if you did that. But the point is that you can get them added into your workload through no fault of your own. And so you want to have some way of measuring it. All right. So then sometimes you get the suggestion you should replace them with these scoped values. And that turns out not to be really true. These scope values are nice if you want to have the same effects, but they're not a drop-in replacement. And they, in fact, they give you essentially no efficiency gain in the normal case. There's two kinds of thread locals, regular ones and inheritable ones. And the inheritable ones are the ones that are really costly if you further spawn subthreads. So in order to save with scope values, you need to have two things. You need to actually have inheritable thread locals. The one from Quarkus, for example, is not. And B, you need to then actively propagate them into further subthreads. You would know if you were doing that. It's not a common kind of thing. So I, again, can't show you in the interest of time how this works with an actual program, but you can easily run it. And the truth is that the memory saving, there's some memory saving, but it's minimal. So the scope values are not really a solution for you to replace the pain of thread locals. You would have to manage them on another level, or more likely have your framework supplier manage them on another level. If you wanted to do it for your own code, it's very unlikely that you are going to be in a situation unless you develop your own framework that you want to use those. So, in conclusion, so I have a couple of minutes for question. If your workloads keep all cores busy, don't use virtual threads. You get increased throughput with tasks that block a lot. You get that sweet direct programming model that you want. You don't really have to do too much thinking if you use something like Spring Boot or Quarkus. They have figured this out for you. Resource overload may be an issue if you're branching out to third-party resources that you are not currently already controlling. Pinning may be an issue. You need to have someone on your team who knows how to watch out for it. It'll be much less of an issue after Java 24. And yeah, if you actually do branching out into further concurrent tasks, into further threads in your own code, structured tasks are great. Otherwise, you may never use them. And, you should understand the weight of thread locals, or at least be aware that someone needs to know how to measure them, and maybe consider scope values, but it's pretty unlikely. And as always, observe and measure. You'll find some tools in the talk here. So I have a few seconds for Q&A. Let's see how this Slido thing is working out. All right. So are virtual threads a good solution to improve code that use a scheduled executor service with schedule at fixed rate? Well, if you, I mean, it's easy enough to kind of run your own, but if right now, I mean, maybe not, right? Because if you're just saying, oh, I want to do this thing every 10 minutes, and that thing that you are doing, you know, is a one thing, then there's no particular need for it. If on the other hand, in every single request that comes in, you might want to do it, but that's kind of less likely a use case. So I would say that's probably not its sweet spot. Do they use the CDI context like platform threads do? They certainly do, because the CDI context is not an inheritable thread local. So in that case, if you're in a situation that you are in a request scope bean and now you branch off from there into other threads, then that's when scope values become interesting. So would it be bad practice to use virtual threads in completable futures? I think the question is, why are you using completable futures? Normally the reason people use completable futures is because they are told you need to do something reactive. Why are you doing something reactive is probably because you want to get better throughput. So I would throw out the reactive part. You know, you can keep it in place and not touch it, but if it is something that's being continuously worked on, you surely feel the pain, and you might just want to, instead of using use virtual threads. You sometimes use a small carrier thread pool also to limit the number of concurrent jobs. See, that is the thing. There's no way that virtual threads by themselves do that. You have to have some other mechanism. So you might want to make it so that you have a queue of pending tasks, and then you have another thread that peels off those. Or you just use a semaphore and have the virtual threads run against it, and they all block until the count is again good enough. You do have to come up with some other construct for that. Game over Kotlin. Well, Kotlin does something different, and it does reactive behind the scenes, so to speak, and it gives you a programming model that makes that somewhat easier. It's not that, the performance is good. They don't, for example, have the issue of overwhelming the garbage collector. If you had too many concurrent virtual threads. The big trouble with that kind of model is that now whenever you have a service, you need to worry, is it async or is it synchronous? And you basically double the size of your API. And it's just unpleasant. But certainly I would not now go to Kotlin just for the reason of doing async. I think if you're doing Java and you like Java, then you now have a perfectly good and maybe an even better solution to do that kind of blocking concurrency in Java. Does setting a thread local inside a virtual thread pin it to the native thread? No, that would be terrible. Okay, did I get everything? Okay, those were a bunch of good questions. Oh, which operations that block allow concurrency? I guess I'm not sure. If the operation blocks, interrupting. When it blocks, you can interrupt. So, like if you, and this happens with structured concurrency, definitely. You might have a few threads that you want to run together, and then they block until some result is ready. And now if one of the results are already good enough for you, then you can make it so that the scope gets interrupted. That will interrupt each of the blocking threads, and they will reliably terminate. Just like today when you call sleep or socket IO, you can block those. The only ones that you cannot interrupt are the ones that do like file IO or other native operations. Okay. That's it. Someone needs this room in 10 minutes, so if you have more questions, just catch me in the hallway. Thank you.